Hi guys, welcome to a lesson of partial differential equations. So in the previous classes, we discussed about the homogeneous and non-homogeneous Drichlet and Neumann boundary conditions. So in this lesson, we are going to discuss about the mixed boundary conditions. As we said earlier, that this is a combination of Drichlet and Neumann boundary conditions, right? So first we will talk about the homogeneous mixed boundary conditions. So here you can see that these boundary conditions are homogeneous boundary conditions, and one of the condition is Drichlet boundary condition, and the other condition is Newman's condition, right? Because the derivative is given at the boundaries. So and the initial condition is also given here. So now we can construct the phenomena of solution. We know that for homogeneous boundary conditions, we start from the separation of variables, and then we talk about the cases, right? Three cases, that is for lambda is equals to 0, lambda is greater than 0, and lambda is less than 0. So here we separated the variables by assuming that u is a function of x and t. So therefore, here ut is equals to xt prime and u double x is equals to x double prime t. And then we separated the variables, and we said that these are the ratios, so they are equals to some constant, right? So when they are equals to some constant, then we said that these are independently equal to the constant respectively, right? So we can write in this form: is equals to lambda, and x double prime over x is equals to lambda. So now we will start with the case one, that is at lambda is equals to 0. So here we can see that when lambda is equals to 0, so x will be equals to c1x plus c2, because we know that x double prime will be equals to 0. And when we will integrate this twice, so we'll get x is equals to c1x plus c2. Then we are given with boundary condition, that is u of 0 comma t is equals to 0, and then ux of l comma t is equals to 0, right? So we have one derivative boundary condition, so we will solve for the derivative, and then x prime will be equals to c1 when we will differentiate this equation. Let's say this is equation 1. All right, so now we will apply the boundary conditions. So from here we can see that x of 0 is equals to 0 and x prime of L is equals to 0, right? So we will apply the two boundary conditions respectively. And from here we can see that u of 0 is equal, 0 comma t is 0. That means that x of 0 is 0. And then ux of L comma t is 0. It means that x prime of L is 0, right? So from here, we will get C2 is equals to 0 and C1 is equals to 0. So it means that this is a trivial solution, and we know that we have to work for a non-trivial solution. So now we will check for case 2, that is lambda is greater than 0. So we already talked about this, that when lambda is greater than 0, then we assign such a value for lambda that should be positive always. That's why we call it as p square, right? So you can take it as k square, mu square, or anything, right? So it should be a positive. So we will raise constant to the power of 2, and we know that that will be always positive, right? So we will find the solution for x double prime is equals to p square x, and when we will solve this equation, this is a second order differential equation. When we solve this equation, we will get these this solution, right? And now we have a boundary condition, so we have to calculate the derivative also. And here the derivative will be x prime is equals to pc4 e to the power px minus pc5 e to the power negative px. And then when we will solve for the t, we will get this solution, right? Because t prime over t is equals to, sorry, 1 over c square will be equals to p square, right? So from here, we'll get this solution. And now we can apply the boundary conditions to these two equations. And here we will apply the boundary conditions. First of all, x of 0 is 0. So it will give C4 plus C5 is equals to 0. And when we call it as equation number 1, and then x prime of L is equals to 0, it will give PC4 e to the power PL minus PC5 e to the power negative PL is equals to 0, right? So we'll call it as equation number 2. And when we will solve these two equations simultaneously, so we'll get C4 and C5 as 0. So again, we have a trivial solution, right? So now we are looking for a non-trivial solution. So we will check case 3. Can we get a non-trivial solution or not? So here is case 3 when lambda is less than 0. That's why we assume it has lambda is equals to negative p square, right? Then the equations will be x double prime is equals to negative p square x, and t prime will be equals to c square p square t, right? Negative. So from these, solving these two equations, we will get the following results, right? Uh, for x, this will be the result, and for t, this will be the result, right? And then we will again calculate the derivative for x. That will be negative ap sine px plus bp cos px. And then we will apply the boundary conditions. So we'll apply the first condition. We'll get a is equals to 0 from here, from this equation, because it will be x is equals to a cos 0 and b sine 0, right? It will be equals to 0. So this is 0, therefore this is 1. And from here we will get a is equals to 0, right? Then we will apply the second boundary condition on the derivative here. So we will get bp cos pl is equals to 0. Then we know that it means that this cos pl is equals to 0, because this bp cannot be equals to 0, right? So cos pl is equals to 0. It means that pl is equals to cos inverse 0, right? So cos inverse 0 is equals to 2n plus 1 pi over 2, right? So uh, we can check it also. We write it in this form because we need a journal form, right? So for n is equals to 1, it will be cos, uh, let me write here. For n is equals to 1, it will be 3 pi over 2. All right. First of all, let's check for n is equals to 0, right? So for n is equals to 0, it will be pi over 2. Cos pi over 2 is 0. For n is equals to 1, it will be 3 pi over 2. 3 pi over 2 is again 0. And similarly, for n is equals to 2, it will be 5 pi by 2. So it cos of 5 pi by 2 is again 0, right? So in this way, uh, we will get always 0 for this value of cosine, right? Cosine 2n plus 1 pi over 2. So p will be equals to 2n plus 1 pi over 2l. All right. And so we will plug this value of p in the equations of x and t. Then we will write it combinedly. So x will be equals to b sine 2n plus 1 pi x over 2l. And uh, t will be equals to, here we can write t will be equals to d e to the power negative 2n plus 1 pi c over l squared times t, right? So here we write, here this is the exponential of this whole function, right? So now we can combinedly write dd as sum of bn from 1 to infinity. So we construct a general solution of this form. Now we will apply the initial condition which is given in the question, that is u of x comma 0 is equals to 0. So it can be any function of x, right? Either a trigonometric function or a polynomial function or exponential function, right? So it can be any function of x, right? So u of x comma 0, when we'll apply, so this will be to the power 0, that is 1, right? This will be to the power 0 because of this t here. When we put t is equals to 0, so this will be e to the power 0 is equals to 1, right? So function of x will be equals to summation n is equals to 1 to infinity bn sine of this function. So now we will generate a Fourier series, and we know that bn will be given by 2 over L integral 0 to L f of x sine 2n plus 1 pi x over 2L dx, right? So now we are assuming that u of x comma 0 is equals to x. So we'll solve for it. We will apply the by part rule here, right? In this function, we can apply the by part rule. So in the next step, we have solved it for the by part rule, right? So it will be negative x times cosine of the angle divided by the angle plus sine of the angle divided by the angle squared. This will be the integral of this function, right? This function. So now we will apply the boundary conditions, and again, we know that this will become cosine 2n plus 1 pi over 2, right? So this cosine 2n plus 1 pi over 2 is 0, and this will be sine 2n plus 1 pi over 2. So this is equals to negative 1 to the power n, right? So we can write negative 1 to the power n instead of this whole, right? This one, right? So here we can write, so uh, here we can write negative 1 to the power n instead of this whole, right? So we'll write it as negative 1 to the power n. All right, so in the next step also we can do that to save the time and save the area, right? And it's looks good to write in a short form. And again, here also we can do that. This is negative 1 to the power n. So we can write it as negative 1 to the power n, right? Negative 1 to the power n. So this is the particular solution of the given homogeneous heat equation for the homogeneous mixed boundary conditions, right? So we can solve it for any initial value, whatever the initial value is given. So we have also already constructed the general solution in the above part, and after that we can just find the integral for bn, and we have to plug in place of bn, and maybe we will get the particular solution, right? So now in the next part, we will talk about the inhomogeneous mixed boundary conditions for heat equation, right? And we already know that in the previous boundary condition, the previous cases of the Drichlet non-homogeneous and Neumann's non-homogeneous boundary conditions, we know that whenever the boundary conditions are non-homogeneous, then we have to construct a steady state temperature, right? So we'll always have a steady state temperature, and so we'll follow the method of steady state temperature. So here we can say that now u of x comma t will be equals to w of x comma t plus v of x, right? So here we can see that, and we know that for a steady state, dou u or dou t is equals to 0. So now the problem is simplified to this form, right? C squared times dou y square u or dou x square is equals to 0. So this is only a function of x, right? So we can write it in this form: d square v over dx square is equals to 0, right? So this is a second order differential equation. We can integrate this equation twice to get the value of v in terms of x. So this is the function v in terms of x, and then we will apply the boundary conditions. So the boundary conditions are u of 0 comma t is equals to a, and ux of l comma t is equals to b, right? So here one of the condition is the derivative boundary condition, so we have to find the derivative. So this will be v prime is equals to c1, and from here we can see that x of 0 is equals to a and x prime of l is equals to b, right? So we'll apply the boundary conditions here. V of 0 is equals to a, it means that c2 is equals to a, so c2 is equals to a, and v prime of l is equals to b, it means that c1 is equals to b. All right, so the general steady state solution is v is equals to bx plus a. Now we will work out for the transient temperature. So now the equation will be reduced to this form, and the boundary conditions will also be homogeneous, right? So because w of 0 comma t is equals to u of 0 comma t minus v of 0, so u of 0 comma t, we already know that it's a, and v of 0 is also a, so a minus a will be 0, this will cancel out. Again, for wx l comma t is equals to ux l comma t minus v prime of L. So UXLT is B, V prime of L is B, so B and B will cancel out, it will be 0. And for the initial condition, now it will be Wx comma 0 is equals to Ux comma 0 minus Vx. Ux comma 0 is given as f of x, and this is our V of x, right? So now we know that the solution for this problem is we only get the solution for the third case. All right, so we will get the solution for the case 3, because for case 1 we will have a trivial solution, and case 2 also we will have a trivial solution, right? As we have already seen in case of the homogeneous Drichlet boundary homogeneous mixed boundary conditions. Here we can see that we constructed the solution in this part. In this part, we can see that for lambda is equals to 0, it was a trivial solution. All right, and this was for lambda is equals to 0, trivial solution here. And again, for lambda is equals to lambda greater than 0, again it was a trivial solution. So we only got the solution for lambda less than 0. That was this general solution, right? So we can directly write there that this is the general solution to save our time. X is equals to this function, t is equals to this function, and we will apply the boundary conditions, and we will get this, right? And this is the same as the problem of the homogeneous mixed boundary conditions, right? So we don't need to calculate, we can write it directly, right? So you can write it this directly. So now we will apply the initial condition, that is wx comma 0 is equals to f of x minus bx minus a, right? So we'll apply the condition. We can call it f of x minus bx is equals to a as gx. So now it will be g of x times sine of 2n plus 1 pi x over 2l, right? So now we can solve it for any function of x, and the general solution will be then equals to u of x comma t is equals to w x comma t plus vx by using the principle of superposition. So this is the steady state temperature and this is the transient state temperature, right? So by adding them, we will get the particular solution to this problem. So this is the method to solve the homogeneous heat problem for different type of boundary conditions. We already discussed six type of boundary conditions, three homogeneous and three non-homogeneous boundary conditions. And now in the next lessons, we will talk about the non-homogeneous heat equation for different boundary conditions, right? So hope you guys understand this lesson well and it will be helpful in your academics. So thank you for watching the lesson. Goodbye.